So yeah, like Piotr did like his preparation for a talk in 2 minutes. So it obviously was fast. Like I'm not sure it was correct, but it definitely was fast. So welcome, Piotr. Woo!
Right, I'm really excited to be here, but before we start, can I have a selfie with everyone? Just say hello and woohoo! Thanks. Right. Okay, so today I would like to talk to you about thinking of software beyond just correctness. And you might find during my talk some life-altering experiences, and if that happens, you can tweet at me at Piotr Murach. You can find me on the GitHub here, and this is my personal website. So this is as much as I'm going to say about myself. So let's dig into it. Find Machine is a Ruby library that I've created to manage state machines in Ruby without any ORMs. It has an intuitive DSL. You can create states, define transitions, and trigger callbacks on those transitions. For instance, you can check for a current state, and then trigger transition to go from red to yellow. Nothing complex. One day, I decided to do a bunch of refactoring to make it more maintainable. So all my unit and integration tests passed. So I decided it's time to release the new version from 0.10.2 to 0.11. Oops. So I've introduced something, and this helpful person advised me that it appears there's a memory leak in the version 0.11 series of the gem. When we bumped to it in our app, we started to experience severe memory issues in production. Oops. He was so helpful as to provide me a simple script to replicate the issue and see the ballooning memory. One of the culprits, the culprit was the event queue. This is where, if you remember, when I was transitioning from red to yellow, I was storing all the events in the event queue and firing a thread, a background thread. But the problem was that this background thread was never killed. So when the finite machine went out of scope, the memory kept on growing. So I decided to temporarily fix it by using object finalizer to manually kill the event queue. But I wasn't really satisfied with the solution. And this event kind of prompted me to think about writing correct software might not be enough. It might help you to create something that doesn't regress into complete mess, but it will not guarantee a performance or issues that I've experienced, because all my tests passed. I had every reason to release the library, but yet I pretty much screwed someone's production system. So I kind of started to think that this kind of situations, lack of visibility, and especially thinking about other developers who are writing code every day, they might be releasing libraries that are progressively getting slower and refactoring their code into slow turtle. So today I would like to show you the idea of performance testing as another way to add a tool to your development tool belt. Chris Seaton, in his PhD, discusses a PSD library, in particular this clamp method, which limits the value between two extremes. This is not particularly complex code. But this method was called thousands of times in the PSD library, causing huge performance issues. And I decided to look at Aspect as my favorite testing framework that allows you to write English-like assertions. I decided to combine that expressiveness with the idea of performance testing. And the way I decided to look at the performance of code is through execution speed, which is basically how fast your code runs. resources usage, which is to do with how much memory you allocate and how many objects. And finally, the idea of scalability. If you increase workloads for your code, method, whatever it is, how does it behave? Is it getting progressively slower? So let's start with a vanilla spec helper. Require the library aspect benchmark, and include aspect benchmark matches to make all the performance matches available in your test suite. It's a module, so you can include it in any test method. Let's describe, because in a TDD spirit, obviously we want to start with a test, but the question is, what assertions do we write? I'm glad you've asked that question. So at the moment, I'm going to put a placeholder because I have no clue. I'm going to call the method in a block and pass it some values. Those values test the extreme case. And then I'm going to use performant least matcher to set expectations of actually how many iterations per second can I execute this method in. Let's say I decide that this method is going to have 2 million iterations per second because I have no idea, I have to start somewhere. And I run my tests, and I get a failure message, which actually gives me the actual number of iterations performed when I call this method, which is below the 2 million that I guessed. And this leads me to some performance caveats. First of all, if you look at the actual value, it's 1.8 million. If I were to use strict values for my performance testing, it would set false alarms. You know, every time you run it, a few iterations, you will experience a difference in the iterations. But to light values, you're actually not going to catch any regressions. So if you give a small number of iterations, you will always pass. So bearing all those things in mind, I decide to set the boundary value to 1.5 million values, iterations per second. OK, so this is the performance of clamp method. Now I'm going to try to write a clamp fast idea. So I start with a clamp fast method and exactly the same implementation. And at this point, when we try to refactor any code to be faster, we are talking about fundamental changes. And these could be as simple as introduction of a different data structure, let's say hash in terms of some complex data structures, or maybe different algorithm. Sometimes a loop is all you need in place of recursion. Obviously, in this instance, I remove all the spurious allocations by introducing just a ternary operator. I believe this to be the optimization. Let's confirm that. I had previously 2 million iterations. Let's double that. Another guess, but hopefully it's faster. I ran it, and it succeeds. OK. How about we do the 4 times the original performance and run it again? OK, we get 7.5 million iterations. That's really good. That's so much faster. So thinking about the caveats, we decide to set it to 7 million, and we captured our method's performance. But is that really what we want to do? You can ask yourself. Because fundamentally, when we run the code, we want to know that it's faster by an order of magnitude than the previous code. We are moving ahead. So you don't have to do any maths in your head. You can use those 2 matches, which is perform faster than and perform slower than, to assign 2 bits of code. And you can also quantify how much faster something is by using once, twice, exactly, at least, and at most matches. This should be familiar to anyone who codes in RSpec. So to remove all the pain of coming up with the how many times this method is faster, we can write this assertion, which asserts that the new implementation is 3.5 times faster than the old one on the latest Ruby. OK, that's good. But this is about how fast something is. But if you recall finite machine, that wasn't exactly the problem. It would manifest itself in speed as well, but predominantly there was ballooning memory. And that's something that I couldn't detect, at least not automatically. So another way to look at the method performance is resources usage. Let's look at the same method that we had before. And now if you look at it from the point of view of object allocations and memory allocations, you can see that there's probably something going on here. There's an array, and we are sorting it, and then we are taking the middle element. So again, TDD spirit, we write a test. Obviously we know the method, but hey-ho. We don't know how many actually objects we allocate here. But let's say we think array allocates maybe one object, and maybe using integer allocates some sort of memory. Let's say we allocate 2 objects. We run that, and we find out that there is actually 3 objects allocated. That's different to what we thought originally. Okay, let's assume there's 3, and we run the test, and it all pass, but we kind of feel cheated because we still, as engineers, we want to know what is going on, why so many objects. So another way to use perform allocation match is to actually specify the type of object and how many times it appears. This is the upper bound, because different implementations of Ruby will have maybe not implementation versions will have different performance, and different platforms will behave differently. But those are internals of Ruby. So we put our assertion again with more detail and run it. And it tells us that actually we expected 1 array, 1 integer, but we get 3 array allocations. So actually the integer means it's not allocated. Actually sorting array allocates more arrays. So that's where the performance issue is creeping in. So we adjust our assertions to 3 arrays, and it passes. We use that assertion, and as you can see, I've added objects matcher, which instructs perform allocation that we are actually talking about counting objects rather than memory. We run this, and our new fast method allocates no objects. That is actually good. We change our assertion to match our error message, and we also can specify that it allocates no memory. So that's nice. We can now write assertions for speed and also for memory. The final step is scalability, which is how much our method, class, objects, whatever, can take. Scalability quite often is thought of as computational complexity. I like to think about it as performance surprises. You run some code, and it performs very well. You run it on bigger batch of numbers, and suddenly grinds to a halt or brings down your server. I've been there. But to talk about it, we need to talk about big O notation. But this is not a class on big O notation. It's a quick dive in. The extra time needed to introduce O notation is amply repaid by the simplifications that occur later. Big O notation allows us to be sloppy, but in a satisfactorily controlled way. Donald Knuth. I like simplifications, and I like being sloppy. That fits my life. So big O notation, really, if you have to think about it, you have messy maths, and you want to find a pragmatic way of talking to other computer programmers. That's all it is. You can imagine it as we have a bunch of points, data points across X and Y axis. In this case, we are looking at life expectancy in the US from 1900 in 10-year periods. And we try usually find a tendency of all these points. In this case, we find a line, and we usually, in big O, this line is called logarithmic. And this is actually a quite good line. It's steep at the beginning for small inputs, and then it tapers off later on. We want our code, we want our methods to behave at least this way. And we note it as log n, where the n is parameter. So let's look at the other situation of mobile subscribers in US between 1880 and 1997. The line is kind of flipped. All the points are flipped from the previous example. We start very slowly, but then we speed up and the curve goes up pretty quickly. And this obviously gives us intuition that our code should not behave this way. We fit a line into this, and quite often in research, this line is thought of as power law line. But in this example, this is quadratic, n to the power 2. And we don't want to be there. It's usually loop in a loop example. I suppose it's important to understand that just having loop in a loop is not a bad thing. If you have limited lists and you know it's always 10 elements, there's no point optimizing that. But if it's going to be growing unbounded, you have a huge problem on your shoulders. So generally, you don't want to be in red. You don't want your algorithm to be growing unbounded. You want to be logarithmic, linear, if you must. So this is all theory, but what about practice? How do we measure that in practice? Measuring empirical computational complexity is a paper from Stanford University that basically tells you how to do it. They test tools like GCC compiler for C or bzip compression tool, and they treat code as black boxes and just observe all the outputs and make predictions about them. And they actually found some bugs in bzip. So I got inspired. I created benchmark trend, which pretty much does what you saw on the graphs, which is takes a bunch of data points and tells you, well, I think it's linear given what you provided me. It adds certain complexity, but we're not going to talk about it. It's enough to know that it powers another set of matches, which is perform constant logarithmic linear power exponential. I kind of feel like those matches are enough to assert scalability of a given code. When you test for scalability, there's a certain algorithm that I tend to follow. It's not particularly revolutionary, but helps me to think about what I'm doing. So first, we need to choose a method class, choose workloads. That's more interesting. We want to choose some exponentially growing data points for testing. Then we somehow want to translate those data points to what our method class program understands. And finally, we want to assert what is the big O notation for the particular piece of code. So recently, I've implemented a Merkle tree. It's an interesting data structure. Helps you summarize data sets. It's used in Git, Cassandra, and Bitcoin. This is my wonderful ASCII art. At the bottom, you have all the leaves. That's what matters for this discussion. Usually those are signatures, one-time signatures, and then you have Merkle root, which summarizes all of that. So if you have Merkle root, you can validate all the transactions in Bitcoin. That's all you need to know. So we know we want to test how fast we can build a Merkle tree. So this is our first point. We know what we're going to test. And we make prediction that it kind of scales linearly with all the leaf nodes. But first, we need to generate some data points. I provide you with bench range helper to make that simple. In this case, we're going to produce those data points that grow exponentially. And the next step is to translate those points into what Merkle tree understands. So for instance, if you have a file understands bytes. Merkle tree understands nodes. So let's translate that. We map all the data points through arrays of L1, L2, L3 nodes, and we create messages, which is array of arrays. Then we expect the Merkle tree to perform linear, but there's a difference. In the past, we just expected some code to behave one way. In this case, we want to call Merkle tree with different inputs. How do we do that? We use the in-range matcher, which allows us to instruct the perform linear about the range that we're going to iterate over. the expect block, if you notice, exposes the actual range number and also the data point that we're looking at. From this on, it's pretty straightforward. Splat messages to the Merkle tree and run the code. And it does indeed perform linear. So we talked about measuring and asserting expectations in our code. But the question is obviously, so what do you actually choose as a subject of your performance assertion? And that's potentially another big topic in itself. But I like to think that you run some profiler on top of your system and you figure out where much of the time is spent. And usually that will be associated with something in your code. It could be a method, like the clamp method, or it could be a class with a lot of collaborators, like Merkle tree. What is important, you find that unit of work that is clearly responsible for your performance issue. Pretty much everyone knows this statement. Premature optimization is the root of all evil. And I find that a lot, especially Ruby developers, like to focus on design first and believe that the performance will be taken care of itself. And hopefully Koichi-san, Mama-san, and Aaron-san will improve the VM, so it's going to be so fast that my code will scale straight away. But it's interesting to look at this quote in the context. I'll read it out to you. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs. And those attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. We should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. So, don't think about trivial optimizations, but definitely do some measurements. Find the most critical things where you get the order of magnitude performance increase, like was the example of clamp method. That single method improved the whole library immensely. A good programmer will not be lulled into complacency by such reasoning. He will be wise to look carefully at the critical code, but only after that code has been identified. Donald Knuth. So finding the critical path and the unit of work that relates to that is the way to do performance testing. But intuition is not a reliable indicator for performance improvements. So just the feeling that you have about code is going to be faster, slower, it's not the way to do performance. I sometimes have conversations about people saying, oh, you should use single codes because they are faster. Right, okay, interesting. How about we use benchmark APIs library and measure this? And we actually figured out that actually it makes no difference. So it's purely stylistic thing. It's naive to think that interpolation somehow slows things down. Obviously, Ruby VM is far more intelligent to figure this stuff out. So there you go. Don't do it unless there's a code standard in your company that enforces that, Rubocop. So what I'm trying to say here, it's good to know your Ruby. There's a fantastic talk about writing fast Ruby by Michael Ober, who talked at a conference in Portugal I attended. And he kind of compares all the standard methods in Ruby. For instance, he shows that a lot of people use gsubs to substitute strings, but you could use tr method, which is five times faster. So if you're writing a library, a code that needs to do a lot of string substitutions, you should probably know that. But check this. So, okay, you might not be convinced. Maybe what happened to me with finite state machine and my experience is just like me just being really awkward developer, but you just write perfect code, it's fast, there's no problem. So if you look at the research of Java and C open source programs, you find that performance bugs are the hardest and take the longest time to fix. So maybe that will prove to you that maybe you have these issues, but you probably don't know about them. I like to think about software in these three categories of correctness, design, and speed. And in Ruby community, we like correctness and design. We fervently practice TDD, and we argue about all the old practices, what is better. But we hardly ever think about speed, and usually see speed as evil. It's going to convert my code, beautiful Ruby, into C-like code. So we try to forget about that. But also my experience showed me that if you build a huge elephant, you're not going to optimize it into cheetah. You might naively think that maybe at the end you're going to tweak a few bits and optimize them, but actually that's a very difficult job to do. I would like to make a distinction between optimization and design. Optimization is kind of trying to fix some bottlenecks at the end. But design for optimization is about thinking what you're going to do before you start writing your library. It might be a requirement from your clients. We're going to build something that's actually fast as a requirement, or we're going to build something and we don't care how fast it works. It's important to think about it. FastJSON API, a library from Netflix that uses my expectations, set out to be fast. And they compared themselves to, for instance, active model serializations, and they are 25 times faster. And that impacts their design, you know. How many objects you have, how many allocations you have. So it's important design goal as much as anything. So I like to think that there is a balance between all these three things. It's not necessarily designing only for speed, but being cognizant of that. I have some key takeaways. They are not very profound, but they help me write faster software. So hopefully I convince you that you should test before optimizing. Your intuition is not a good predictor of how your code is going to behave. And hopefully you appreciate that beautiful and correct code doesn't have to be at odds with speed. And finally, even with a simple clamp method, simpler code tends to be faster. Some of the things that I've said might sound kind of naive, maybe ridiculous, but if I achieved something today, I hope to make you think more about this speed nature of your code. And here are all the research papers that I refer to. Thank you very much. It was a pleasure.
Thank you. So, questions?
Have time for questions.
Not really? Yeah.
So, in order to prevent that you have these kinds of performance issues, can you do something in advance to be able to identify what part of the code you should test? Or so how could we approach you that to avoid that these kind of things happen before they have happened?
Right, so I definitely don't advocate to write code purely with performance in mind. I would start with obviously gathering the requirements of your system. So if you are implementing something, just first implement that. And then, ideally, there's a lot of stackprof, a lot of profilers that you can run, because obviously it depends what you're writing. If you're writing a Ruby gem, or you're writing a Rails application, because in Rails, you have a whole plethora of things that you can think about, like, you know, there's research papers that talk about active record APIs, which people quite naively use, which translate to really, really bad code and really poor performance, like doing where queries when they fetch 1,000 records and then pick one instead of just fetching one record. So I still would say try to write the code and then run the tool on top of it and then write your tests. At least that would be my approach. Don't start too early. Premature optimization, the advice is not necessary because you're still figuring out stuff out. But once you are certain what you're doing, then I think it's a good point to pick out those tools. And for instance, I write a separate folder called performance, and in that folder, so I have unit, integration, and performance. And in performance, I write those tests because you don't necessarily want to run them all the time, but you want to run them maybe on your CI. And let those guide you. Obviously, you also don't have tests that kind of look at the whole system, because then what you're going to pick, it's like, I've got 100 active record models, what do I pick? So localized work of unit is also important. I hope that answers.
All right, one more here.
Do we have some function to measure the allocation increment function with example of this complexity like in speed?
No, the answer is no, I don't have at the moment, but
yeah,
it's open source,
but
so
it's possible, huh?
Yeah, it's one angle to look at it. Yeah.
All right.
So like, if we scale how many more objects and etc. Yeah. So.
All right. More questions? For every question you get a card and you can win the ticket. One here.
By the way, all my stuff is open source, so by all means check it out and contribute. This is all for you guys as well as for me. So. Hello.
Hello, Piotr. Thank you for your talk. So my question is, have you tried to do something like Simple Cov does, like hacking into RSpec and doing some measurements automatically, storing some history of, I don't know, how many allocations are performed in each of your ordinary RSpec tests, and warning user about it increases a lot? Because it is not. It took time to write all these performance tests, but if we could do something automatically, it would be convenient.
So currently, I don't have that. I consider that for the future development. Not exactly what you said, but pretty close. Yeah, I would like to work on that. I think it's a good idea.
Thank you.
And the last question, right there.
Wait.
Thank you for your talk. My question regarding this measurement you showed on your first slides about interaction per second, right? And as far as I understand, this number will be different on different machines, right? So
In different what?
on different machines.
Yeah.
On different computers, right? So does it mean I strongly recommend it to measure difference in time between two methods to implementation rather than amount of those interactions per second? Is it correct, or correct me if I'm being wrong here?
I mean, it is correct. There is obviously inherent problem in testing time, and you're right. In different, maybe different versions of Ruby, you will have different performance. There's also a few matches that I didn't show that allow you to smooth out all the numbers by increasing the sampling of all the measurements, which usually creates a more stable test suite. For instance, you can, like in Scalability, you can say run everything hundreds of times for each data point. So we don't have, we kind of throw out the outliers from our measurements. But yeah, at the moment it doesn't use CPU time, it's a clock time, but there is a problem, yeah. And your idea could work better in a way because it's less dependent on the system. Right, thank you.
I think that's it. Let's thank Piotr again for his talk.
Right, thank you.